Yogaha Karmasu Kaushalam.
We are going to discuss a topic called parametric test. This will be under the umbrella of the hypothesis testing. When you collect any type of data and then you would like to go for a hypothesis testing, then you will have broadly two types of choices available. One is to go for a parametric test, or the second one is to go for the non-parametric test. So whether to go for a parametric test or non-parametric test, that purely depends upon number one, your research objectives, and number two, your scales of measurement. So whether we'll go for a parametric test or non-parametric test, that depends upon our research objectives as well as the scales of measurement. So friends, in this session, we are going to discuss our topic called parametric test. And within this parametric test, we'll start with the different types of t-test. With the help of software also, we'll demonstrate how to do the test. So let us start with the parametric test. Now just I am sharing my screen. So parametric test, and as a part of the parametric test, we'll start with the t-test. Now first of all, you must have heard this name t-test as a student's t-test. So there is a brief story behind that why it is called a student's t-test. This test was invented by a statistician. His name was W.S. Gossett, and he was a very newly appointed quality control engineer, and his duty was to test the production lot at the end of the day. And after testing based on certain quality parameters, if the production lot is okay, then the entire days of the production was uh, considered to be okay. And if it is not okay, then the entire days of the production is rejected. So that was the practice being adopted by the organization. And he was also following like that. Now, when he was rejecting the lot, he was rejecting the entire days of the lot, right? So he thought that whenever I am rejecting the entire days of the lot, at that time the organization has to bear a huge loss. So why don't I start taking samples at some small interval of time? And if the uh, even if I am just rejecting the lot, then also a very small lot needs to be rejected. So it is perfectly okay. So that was the practice he started. And when he started this practice, he found that whenever his sample size was less than 30, at that time the shape of the distribution was something different from the normal distribution. And at that time, the normal distribution was the only known distribution. We are talking about the year around 1910, like this. So uh, he uh, then calculated everything, and then he came up with some new kind of distribution, and he was very happy. So he went to the organization and then managing those person who is the reporting persons, and then he went there, and then he very happily shared the results that we have invented something new. But the management didn't like this, because uh, Mr. Gossett wanted to publish this work, and management thought that if the work is being published, then definitely our competitor will also learn it. So then management didn't allow him to publish. So he gave some alternative idea. This is a picture of Mr. Gossett. He gave some alternative idea that I will not use my name, I will not use our organization's name. Let me use a word as a student, and let the work being published as a student's work, so that the competitor will not be able to understand that it is our organization's work. So then management also agreed, and then the work was being published as a student's t-test. So he gave a name as a T distribution, and then the work was being popular as a student's t-test. So that is the brief history behind the term, why it is called a student's t-test. And we also understood that originally his experiments were below 30 sample size, right? So originally the t-test was applied when the sample size was less than 30. And in statistical term, it is called a small samples. So a brief bifurcation of the hypothesis test can be understood as a based on sample size less than 30 and greater than 30. And less than 30, we call it as a small sample test, and t-test is one of the small sample test. Now, what was the t distribution that Mr. Gosset found? So, when we try to understand the t distribution, these are the assumptions and requirement. So, the first assumption and requirement is variable x is normally distributed. Now, you may be thinking that just before 1 or 2 minutes, I told you that uh, if the sample size is less than 30, the distribution is not normal. Then why we are talking about that the variable x is normally distributed? Because of the reason is that we understood that a sample size less than 30 is a small sample, sample size greater than 30 is a large sample. And large sample test is a Z test. And it is based on the normal distribution. But to fulfill the requirement of the normal distribution based test, Z test, there is also another requirement. And this requirement is that the population variance should be known to us. So population variance, or in simple terms, suppose if you want to understand that population mean, population variance, population standard deviation, these parameters, population parameters must be known to us. Then only we can go for a Z test. So to apply Z test, we must require two conditions. Number one, obviously sample size greater than 30. But number two, the population parameter must be known to us. But many a times, practically, when we are collecting the data, our sample size is greater than 30 and population parameter is not known to us. We don't know what is population mean. We don't know what is population variance, like this. So then what should we do? So the statisticians are recommending that in that situation, you can go for a t-test if the data are normally distributed. So we need to test our variable, that whether it is normally distributed or not, when we are applying a t-test for a sample size greater than 30. If we are applying a t-test for a sample size less than 30, then obviously it is understood that the variable needs not to be a normally distributed. But if we are applying it for a sample size greater than 30, then we have to test the normality. So this first assumption is applicable when we are applying it for a sample size greater than 30. And in all statistical methods, we are assuming that samples must be collected randomly. So randomness of the sample is also applicable equally here. As soon as the sample size becoming greater than 30, at that time the distribution is becoming approximately normal. So it is very similar to Z distribution as sample size gets large, 30 plus. Now the variance, fourth one, the variance of the two groups is not different, and if different, use alternative formula. So what do we mean by this? So basically there are two formulas. Formula number 1 is applicable when the variances of the two groups is equal. And formula number 2 is applicable when the variances of the two group is not equal. But what do we mean by equality of variance? Variances are equal and variances are not equal. What do we mean by this? Let us try to understand. So variance means variability. Variability in the data. Say for example, we are comparing the two age groups. And one age group we are identifying as 18 to 25. And second age group we are identifying is 26 to 50 years of the group, right? So 18 to 25 when we talk, so 18 to 25 it is having only 7 years of variability, and 26 to 50 years it is having 25 years of variability. Can we compare these two groups? If a one group is having only 7 years of variability and second group is having a 25 years of variability, how do we compare? There must be some naturally significant difference that is present here, right? So the groups that we are comparing, that must be equally distributed according to the variances. So that is what we mean by the equality of the variances. So there are the test is also available that we can test empirically. The test is known as Leven's test. The test is known as the Leven's test for equality of variances, that we will check. F test is basically applicable. So in my subsequent slide, we'll also, when we'll take the SPSS software and then we'll test the T test, at that time we'll again come back to this assumption of equality of variance, and empiric also will study this one. But at this moment, this assumption is applicable, and there are two formulas. One formula is applicable if the variances is equal. Second formula is applicable when the variances are not equal. And the next assumption is that n minus 1 degree of freedom. Now, every time this degree of freedom is coming, whenever we talk about the sampling theory, and it is very technical term, so let us try to simplify this term, that what do we mean by degree of freedom. So degree of freedom, uh, as the Navratri, maybe when you will see this video, the Navratri maybe it is going on. So during this Navratri period, we Gujaratis would like to wear every day a new dress, right? New clothes. So let us assume that we have at the starting of the first day, we have all 9 dresses are available. Now, so you have 9 choice available on the day 1, right? You can pick up any new dress and then you can move ahead. But the second day, what will be the situation? You have 8 choices available. And at the 9th day, what will be the situation? Only whatever is left, that is available. You do not have any choice. On the last day, 9th day, you do not have any choice. So if the 9 days we are considering, then 9 minus 1, 8 days, you have 8 degrees of freedom to choose the dresses available, clothes available. But on the last day, you do not have any degree of freedom because nothing is left, right? Only whatever is left, that only you have to pick up. So that is the concept of degree of freedom, n minus 1. Whatever sample minus 1, it is your degree of freedom. Now that as a layman we try to understand, but how it is applicable in the t-test. So t-test, say for example, we understood that when the sample size is greater than 30, at that time, when the sample size is greater than 30, at that time the z test is applicable. But we require that the population variance must be known to us. And if the sample size is less than 30, we go for a t-test. Now, with respect to the t-test, we do not have access to the population parameters. So we have to estimate it. So how do we estimate? So the estimation process undergoes in such a way that whatever sample mean, we are fixing it as a population mean. So x bar suppose is our sample mean. So the x bar, whatever the sample mean, we are fixing it as a population mean. And then in how many ways we can obtain that mean. So say for example, we have these 5 samples. Let us try to understand. Is the very simple example that we collected 5 samples, and this sample mean, if we calculate, the sample mean turned out to be 50, 50, right? So 50 is our sample mean. Now this sample mean, we are fixing it as a population mean. So population mean x bar is fixed. So we have x1 plus x2 plus x3 plus x4 plus x5 divided by 5 is equal to 50, right? Now, in how many ways we can get this 50? So we can put any value of x1, x2, x3, x4. But once we fix the values of x1 to x4, we do not have any choices available for x4, x5, because our answer 50 is fixed. Because we cannot change 50. Right, so answer is fixed. So we will have n minus 1 degree of freedom, means 4 values we will be able to fix up, but for the last one we do not have any degree of freedom. So that is how it is being utilized in the t-test. Fine. So let us move ahead. Now if we try to compare the z and t distributions, then how these two distribution will look like. So the uppermost distribution is the normal distribution. And for each of the sample size, the shape of the distribution will be different. So we have this t distribution at degree of freedom is equal to 20. We have this t distribution at degree of freedom is equal to 5, like this. So as the sample size becomes smaller and smaller, the distribution becomes flatter and flatter. As the sample size becomes larger and larger, the distribution tends to become normal. So this is how we can understand the concept on the comparison of z-test and t-test. Now, what exactly we are trying to do in t-test? So let us try to simplify the things. Basically, let us understand that, let us imagine that we choose 2 children at random from the 2 classrooms. There are 2 classrooms. Let us call this classroom as D8 and C1. These are the 2 classrooms available. There are some smiling faces, some children are available. And what we need to do, we need to compare their height. This is our job. Let us imagine that there are 2 classrooms, and then we need to choose 2 children at random from 2 classrooms. And after selecting these 2 children, what we need to do, we need to just compare their height. And obviously, when we compare their height, then we found that one student is taller than the other. One student is taller than the other. Why? What could be the reason? Can you think some reasons that why one student may be taller than the other? So you may be thinking that maybe some genetics. You may be thinking that maybe some age difference, or you maybe have certain other reasons in your mind. All these reasons we can broadly classify into 2 main reasons. Reason number 1 is that there is a significant difference between the 2 groups. So the students in one group are taller than the student in another group. There is a significant difference in the 2 groups. Significant difference means what? Age difference. one group is having a 7 years of age and second group is having a 11 years of age. So obviously the group which is having 11 years of age definitely will have a taller than the 7 years of age, right? So this could be the reason number one. Reason number two can be by chance. By chance, we picked up a shorter student from D8 and a taller one from C1. By chance. Otherwise, age groups are same. Age groups are same. But as we are picking up randomly, so by chance we picked up a taller one from the C1 and shorter one from the D8 group. Right. So when we found a significant difference, how do we ensure that is it because of the reason number one or is it because of the reason number two? How do we ensure that whether the significant difference is found, is it because of the reason number one or is it because of the reason number two? Now, as a researcher, we all are looking for the natural significant difference. We do not want the chance element enter into our results. And reason number two was because of the chance element. By chance, we picked up a shorter one and taller one from the each group, right? And as a researcher, we don't like that the chance element should not enter into the results. So then what should we do to reduce this chance element? So how do we decide that which reason is most likely? And how do we ensure that the chance element should be completely eliminated or it should be reduced? So the what was our sample size? Only one. So what should we do then? Yes, you are thinking right. We need to increase the sample size. We need to increase the sample size. Measure more students. If we increase the sample size, then on an average, we can compare the results. So by increasing the sample size, if there is a significant difference between the two groups, then the average or mean height of the two groups would be very different, right? If there is a significant difference between these two groups, then on an average, the mean height of these two groups would be very different. And if there is no significant difference between these two groups, like this, then the average or mean height of the two groups would be very similar, right? So now you can guess that what exactly we are doing in t-test. So how many groups we are comparing? Yes, we are comparing two groups. We are comparing two groups. So always remember that whenever you want to compare the two groups, at that time t-test will be applicable, number one. And what you are comparing here, we are comparing the height of the children. Now height is what variable? In terms of, if we classify the scales of measurement, then there are four scales of measurement: nominal, ordinal, interval and ratio. So in terms of scales of measurement, height is a ratio variable. So whenever you want to compare any interval or ratio variable of the two groups, at that time t-test will be applicable, even if your sample size is greater than 30, because majority of the time we do not have access to the population parameter, right? In a survey data, majority of the time, if you are working on a survey data, then definitely you need to go for a t-test when you want to compare two groups of mean. So mean comparison, two groups, t-test will be applicable. But remember, these living things normally show a lot of variation also. You are aware that mean alone cannot represent your entire set of data. You require some supporting element along with the mean. So what should be the another parameter to be compared along with the mean. So yes, you are thinking right. You need to add standard deviation or variances. So it is very unlikely that the mean height of the two samples will be exactly same. Right? It is very unlikely. So what should we do? We can analyze the spread of the heights of the students in the sample by drawing histograms. Right? So here we are using a histogram. So we can see that very clearly that the C1 sample and D8 sample. So the spread of the data for C1 sample 140 to 169 and for D8 sample 160 to 189. So just imagine that what is the overlapping categories? The overlapping category is very small, 160 to 169, very small overlap, right? So here the ranges of the two samples have a very small overlap. So the difference between the mean of these two samples is probably significant, right? If we test this, then probably it will turn out to be a very significant difference because a very small overlap. That is the reason. Here you can just observe the range is same 140 to 189, 140 to 189 in both the cases. So there is a huge overlap. All data are having overlap. So the difference of this between these two sample may not be significant, right? So whether the difference is significant or not, along with mean, we need to also add standard deviation. Now, with respect to this t-test, we have three types of t-test. The first one is independent sample t-test. Second one is known as the dependent or paired sample t-test. And third one is known as the one sample t-test. So we'll see these three types of t-tests one by one with SPSS, independent sample t-test, paired sample t-test, and one sample t-test. So before going for independent sample t-test, we need to test the assumption of normality, that if the data are normally distributed or not. And if the data are normally distributed, then we can go for a parametric test called t-test. So for example, in this case. And if the data are not normally distributed, then the procedure is like that. We can switch to the non-parametric test. So how do we test normality then? For that, I am just sharing my screen. To test the normality, this data is regarding the file called independent sample t-test, where we have a variable called monthly mobile bill. Now we are assuming that it is normally distributed, and then we are assuming to go for a t-test. So this assumption needs to be tested empirically. So how to test that whether the data are normal or not? The multiple ways are present to test the normality. One of the ways is to go for the hypothesis testing part. Right? There are ways you can see graphically also that whether the data are normal or not. There are ways in which you can see the certain hypothesis tests are there. Say, for example, Kolmogorov-Smirnov test is present. There is a Shapiro-Wilk test is present. Right. So there are multiple tests are also available depending upon which software you are using. And then you can test empirically. So let us test that whether this monthly mobile bill is normally distributed or not. So to test the normality, we need to click on Analyze, Descriptive Statistics, and the option called Explore. When you click this, then whichever variable you want to test, you need to shift into the dependent list. So we need to test monthly mobile bill. So I have just transferred the monthly mobile bill into the dependent list. Now we need to click on statistics. There is a by default tick mark on the descriptives. We can additionally give a tick mark to outliers. We can click on continue. We can click on plots, where this is a main tick, normality plot with test. This one is the main tick mark, because based on this tick mark only we'll get the results of the hypothesis test. So don't forget to give a tick mark on normality plots with test. Additionally, if you would like to see the histogram, you can give a tick mark for histogram also. You can click on continue. Option, we need not to do anything because we do not have any missing value. And then we need to click on OK. So as soon as we obtain the result of the normality testing, see, there are so many results are present, but with respect to normality and hypothesis testing, this you need to interpret. Test of normality. The test of normality is specifically it is used for the result of the hypothesis testing. Now, what is your null hypothesis here in the case for test of normality? So no matter whatever the type of test that you are using here, the by default available option is the Kolmogorov-Smirnov test and Shapiro-Wilk test. There are other tests are also available, say for example, Jark-Bera test, right? So there are multiple tests available, but depending upon the type of uh, whatever you have software, your null hypothesis will remain same for test of normality, and that is the distribution is normal. The distribution is normal. That is our null hypothesis. So we have the results of this case test. Significant value, it is written 0.200, which is greater than 0.05. Our level of significance we are assuming here as 5% level of significance. So decision rule is we need to compare the significance value with our p-value, that is the 0.20. So if the significance value is less than or equal to 0.05, then reject your null hypothesis at 5% level of significance. If the p-value is less than or equal to 0.05, then reject your null hypothesis at 5% level of significance. And if the p-value is greater than or equal to 0.05, then we fail to reject the null hypothesis. So here the KS test, the p-value is 0.200. For Shapiro-Wilk also, the p-value is 0.063. Both the p-values are greater than 0.05. So our conclusion is that the variable called monthly mobile bill is normally distributed. Right? We fail to reject the null hypothesis, so we can say that the variable is normally distributed. See, perfectly normally distributed variable will never get. You will never get a perfectly normally distributed variable. It is the question that whether the data or the variable can be considered approximately normally distributed or not. That is the concern. So based on this test, yes, we can say that the data can be considered as an approximately normally distributed. So we can confirm the normality and we can move to apply the independent sample t-test for this data. Right. So this is how you can interpret the result of the normality test. Now, if you look at the histogram, say for example, if I double click on this, and if I try to fit the curve, it is a normal. Here it is normal. So you can just observe that when there is a big bar at 410, right? There is a column available 410, which is uh, it is not the perfectly fitting to the normal distributed curve, right? So there are more values at 410, and if you see the 450, then there is no frequency available at 450. So the data, by looking at this histogram, we are not convinced that it is a normally distributed data. But still, as the hypothesis testing is concerned, we are concluding that the data are normally distributed. Right. So it is the approximation that we are obtaining through this test, but otherwise the data is not perfectly normally distributed. But yes, there are uh, maybe 70 to 80% of the data are very nearer to normality. You can just observe the columns which are gradually increasing and then decreasing also. Right. So with this data, we can consider as an approximately normally distributed data. But as the test is saying, the both case test and Shapiro-Wilk test, that the data are normal. So we are concluding that the data are normal and it is suitable to go for the parametric test. Alternatively, from the skewness and kurtosis also, you can conclude that whether your data are normal or not. So here the skewness, what are the range of the acceptable value for the skewness? So it is recommended that the values are in between -3 to +3. The recommended value for skewness, it is -3 to +3. So as minus 0.092, so it is under control. And for kurtosis, there are certain authors who are also recommending -7 to +7. So minus 0.898. So we can consider based on the skewness and kurtosis also that the data are normally distributed. So this is, but skewness and kurtosis, always remember that it is a descriptive measure for the normality. Skewness and kurtosis are the descriptive measure. It is not the hypothesis testing. Hypothesis testing, obviously, it is more reliable as compared to any descriptive or graphical measure. So we are considering this and we can conclude that the data are normal and it is appropriate to go for independent sample t-test for this data. So let us start independent sample t-test with SPSS. So let me share my screen. So you can see here there are two variables. If we see the names of the variable, gender and monthly mobile bill, these are the two variables. The data file is shared with you. You can also practice along with me. Now the two variables, gender and monthly mobile bill, where we have coded male as a 1 and female as a 2. And monthly mobile bill is a scale variable. It is measured in terms of rupees. So gender and monthly mobile bill. Now, first of all, let us discuss that how do we identify that whether we need to go for which type of t-test, because within this three types of this t-test also we need to understand the applicability. So independent sample t-test will be applicable when you have a grouping variable as a dichotomous variable, and second variable we'll call it as a test variable, and test variable as a continuous variable, scale variable. Scale means either it can be interval data or it can be a ratio data, and gender it will be a, it is definitely it's a dichotomous variable. So any two group variable that you want to compare with the continuous variable, then we need to go for independent sample t-test. So here we have considered the gender. It can be the variable for comparison. Suppose you want to compare the marks of the students with respect to two classrooms. You have two classrooms, classroom A or classroom B, maybe you have some grantee-net students, maybe you have some self-finance students, or you have two different sections available, right? And you want to compare marks of a particular subject, same subject, on two different classrooms. So you can go for independent sample t-test. Suppose you want to compare the level of customer satisfaction with respect to two types of banking. So here two types of banks, certain maybe you have one group of bank as a public limited banks, and another group of banks you have a private sector banks, and you want to compare the customer satisfaction of these two types of bank. So here the customer satisfaction, we are assuming it as a scale variable, and two group variable, dichotomous variable as a types of bank. So you can go for independent sample t-test. Similarly, you may have identified some other variables also. Suppose you want to compare the two data of the two states, right? State A versus state B, then also you can go for independent sample t-test. Suppose you want to compare two types of organization where you have large scale organization and medium scale organizations, then also you can go for this independent sample t-test. Suppose you have the data regarding the comparison of two different cities, then also you can go for independent sample t-test, right? So you may have so many situations where you would like to compare your continuous variable, your scale or interval data, your ratio data or interval data across your dichotomous variable, between your dichotomous variable. So then you can go for the independent sample t-test. So how do we go for applying it practically? So we have this data view. So we have gender and monthly mobile bill. And to apply this test, we need to click on analyze menu. Then what exactly we are doing here? We are comparing the mean. If you remember, we are comparing the mean. So it is available in this section, compare mean. And then we have this third choice available, independent sample t-test. So we can click here, independent sample t-test. And then we have gender and monthly mobile bill. So we need to transfer gender as a grouping variable. We need to transfer monthly mobile bill as a test variable. But still this defined group is not active. So we need to click here on gender. Now it is active. We need to click here, define groups. And group 1 is 1 and group 2 is 2. And then continue and then OK. So this is the process. And when we click on OK, we have this output available for the t-test, independent sample t-test. So the first table, it is regarding the group statistics, and second table is regarding the independent sample t-test. Here what we are assuming, as our sample size is 41, what we are assuming that this variable called monthly mobile bill is normally distributed. This is what we are assuming. That is the reason we are going for a t-test, which is a parametric test. This is what we are assuming. Obviously, we can test it also, right? Whether the data is really the normally distributed or not, that we can test it also. So here we applied independent sample t-test, and the first table is regarding the group statistics. So we have a column called gender, then N is our samples, mean value, standard deviation, and standard error of the mean. Now when we see at the mean values 429.05 and 430.52, so a very slightly higher female monthly mobile bill is observed as compared to male monthly mobile bill. We can have 430.52 and 429.05. So very slightly higher female monthly mobile bill is observed as compared to male monthly mobile bill. Standard deviation looks very similar. But whether the mean difference is, can we say that the female are having higher monthly mobile bill as compared to male? Can we say? So that depends upon the uh, results of the t-test. But in a prima facie, from the descriptive statistics, we observe that a very slightly higher female monthly mobile bill is observed. Now, the second table is regarding the independent sample t-test. Now, with respect to that, we have two row available: equal variance assumed and equal variance not assumed. Equal variance assumed and equal variance not assumed. So, if you remember, we discussed that there are two formulas. Formula number A is applicable for equal variance assumed, and formula number B is applicable when the equal variances are not assumed. Right. So how do we know that whether we can assume equal variance or not? So for that we have this test called Leven's test for equality of variance. It is by default available. We have not given any tick mark, but it is by default available in this SPSS. So when you go for independent sample t-test, the by default option, it is considering this Leven's test. So how do we interpret the results? So first of all, we need to understand the null and alternative hypothesis for Leven's test. So for Leven test, the null hypothesis is what? The null hypothesis is that there is no significant difference in the variability of the two groups. There is no significant difference in the variability of the two groups. Which hypothesis we are talking? We are talking about Leven's test and the hypothesis of the Leven test. Please remember this. So hypothesis is what? Null hypothesis is what? There is no significant difference in the variability of the two groups. What does it mean? That equal variance assumed. If there is no significant difference in the variability, ultimately what does it mean? Equal variances are assumed. So your null hypothesis is what? Equal variances are assumed. Now the test statistics, you have this F statistics 0.022. It is called calculated value. F statistics, F calculated. See, whenever you apply any type of test, you will have a calculated value test statistics. For F test, it is your F calculated. For T test, it will be your T calculated. For example, if you are applying a Z test, then it's a Z calculated. If you are applying a chi-square test, then it's a chi-square calculated. So whatever test you are applying, that will be your calculated value. And against each calculated value, there will be a p value, and it is called significant value. So this p value, p stands for probability. So the software has given us a p value which is 0.884. 0.884. What is our level of significance? So generally, as a researcher, you can assume 5% level of significance. Now 5% means what? 0.05. 5% means 0.05. So this is your comparison value. 0.05 you can compare with this significant value which is reported as 0.884. You can see this one, 0.884. Now, is it less than 0.05 or is it greater than 0.05? So it is greater than 0.05. So please remember the thumb rule that if the p value reported by the software is less than or equal to 0.05, reject your null hypothesis at 5% level of significance. If your p value is less than or equal to 0.05, then reject your null hypothesis at 5% level of significance. What is your p value? 0.884. So what is your decision? Your decision will be not to reject the null hypothesis. See, when you report the results of the any hypothesis test, your results will be reported as either number one, you reject the null, and second one, you fail to reject the null. These are the two outcomes. Either you reject the null or you fail to reject the null. In our understanding, in informal discussion, you can discuss that you accept the null, but while reporting the results of the hypothesis testing, you will have to always report as you fail to reject the null. Right? It can be understood as, say, for example, in a court case, the person is guilty or the person is not guilty. But if the person is not guilty, you cannot say the person is innocent. If the person is not guilty, you cannot say the person is innocent, because you do not have enough evidence to declare that person as a guilty, so the person is not guilty. Similarly, while reporting the results of the hypothesis also, same logic can be applied, that either you reject your hypothesis or you fail to reject your hypothesis. So here our p-value for Leven's test, it is 0.884. So we fail to reject the null. It means the statement of the null hypothesis is true. What is the statement? There is no significant difference in the variability of the two groups, means equal variances can be assumed. So the statement is true, you can assume the equal variance. So variability in the monthly mobile bill between male respondent and female respondent is equal. That is what you are concluding from the Leven's test for equality of variance. And it can be also visualized from this standard deviation, which is almost equal for both the groups, 12.30 and 12.56. Right. So this is what we understood as our assumption number one regarding equality of variances. I hope this point is clear. Now, when we are applying this test, t-test, what is our null hypothesis, by the way? The null hypothesis is that there is no significant difference in the monthly mobile bill between male and female respondent. This is null hypothesis that actually we want to test with independent sample t-test. So we have this result of t statistics. Now we have concluded that the equal variance is assumed. So row number one will be applicable, and all the interpretations and reporting will be done for row number one only. Equal variance assumed. Now this, forget this row number two, equal variance not assumed. This value we will not interpret because it is not applicable, right? So we'll interpret only the equal variance assumed, this row number one. Now what is this t value? T value is minus 0.379. It is the answer of this our equation t statistics, that has been, we have this x1 bar minus x2 bar, the difference upon standard error. So this is the t statistics, it is minus 0.379. And at degree of freedom 39. 39 means n1 plus n2 minus 2. We understood that it is n minus 1, but n minus 1 is for one group. If we have two group, then for one group it is n1 minus 1. For another group it is n2 minus 1. And when we combine these two groups, it becomes n1 plus n2 minus 2. Right. So for a sample size of this 41, your degree of freedom will become 39. So this is why it is 39. And what is a significant two-tailed value? 0.707. Remember our thumb rule, 0.05. So it is greater than 0.05. We fail to reject the null hypothesis. So we can conclude that there is no significant difference in the monthly mobile bill between male and female respondents. There is no significant difference in the monthly mobile bill between male and female respondents. So both the genders are having equal monthly mobile bill, and the difference that we have found is just because by
chance. You may be thinking that what is the interpretation of this T calculated? So this T calculated, it is 0.379. It is indicating the mean difference in terms of standard deviations. So the difference or in terms of distance between male mean and female mean is just by a distance of only 0.37 times standard deviation. These two means are away from each other with a distance of 0.37 times standard deviation, which is very less, right? Where these two means are very nearer to each other, and that is the reason that they came up as a the result came up as a no significant difference. If the difference is large, but how much? Up to 1.96 times standard deviation. So if the difference, if the T calculated value is more than 1.96, it will turn out to be a P value which is less than 0.05. Right? So larger the T calculated, smaller the P value. Smaller the T calculated, larger the P value. Here the T calculated is very small, only 0.37. So we have the P value large, greater than 0.05, and it is 0.707. So ultimately what we are concluding here, that both the groups are having equal monthly mobile bill and the difference is not significant. What was the mean difference? The mean difference was only minus 1.47. How do we get this difference? 429.05 minus 430.52. So the mean difference we have obtained, it is coming out as minus 1.47. Now, SPSS has also reported this 95% confidence interval of the difference. So what is that? 95% confidence interval of the difference. And it is reported as minus 9.33 to plus 6.38. So what is that? So let us try to understand. This time what is your mean difference? Minus 1.47. Suppose from the same population we are repeating our research one more time. We are not changing the population and we are repeating the result second time. Will we get the same mean difference of minus 1.47? No, will not get. Right? You will agree that there will be slight change in the mean difference. Though it may be very nearer, but there will be definitely the same mean difference will not get. Suppose third time you are conducting the same experiment from the same population. Will you get a same mean difference? Definitely not, right? So then the question arises in our mind that can we get a range of the difference then? That with some probability, can we get a range of the difference? So yes, this is your range of the difference. That the mean difference with respect to population will lie between minus 9.33 to plus 6.38. The true mean difference will lie between minus 9.33 to plus 6.38. And what is the probability of obtaining the? The probability is 95%. So there is a 95% chance that the mean difference will be in between minus 9.33 to plus 6.38. This is the probability of obtaining a true mean difference. Now lower limit is negative, upper limit is positive. What does it mean? So to understand this, when we get a negative mean difference, what does it mean? When we get a negative mean difference, what does it mean? A negative mean difference, it indicates that the second mean is higher than the first mean. Which is the second mean is this case? Female mean. When we have x1 bar minus x2 bar, if x2 bar value is higher, definitely we'll get a minus value. So second mean value is higher than we'll get a minus value.
So this time the second mean value is a female 430.52, which is higher than 429.05. So when we have a female monthly mobile bill higher than male monthly mobile bill, we'll get a negative difference. But the difference is positive also. Upper limit is positive. What does it mean? That it is by chance this time only we get a female monthly mobile bill higher than male monthly mobile bill, but our 95% confidence interval of the difference, the upper limit is a positive one, so it indicates that maybe sometimes in future there will be some situations where male monthly mobile bill will be higher than your female monthly mobile bill because the upper limit is positive. Right, so a negative and positive upper limit and lower limit can be understood like this. So if both limits are negative, lower and upper, what does it mean? In this case, suppose if both limits are negative, it indicates a significant difference because female monthly mobile bill is higher than the male monthly mobile bill. If both the limits are positive, what does it mean? It will mean in this case, suppose, then a male monthly mobile bill is higher than a female monthly mobile bill. And if one is negative, one is positive, what does it mean? There is no significant difference. In another way, we can also understand that if zero is included in between lower limit and upper limit, if zero is in between, then your conclusion will be there is no significant difference. But if zero is not included, so when the zero will not be included, if the lower limits are and upper limits are both negative or both positive, then the zero will not be present. Right. So in this way, we can understand the independent sample t-test.
Now the second type of t-test that we are showing is paired sample t-test or dependent sample. So let us see already we have seen the independent. Now let us see the dependent sample t-test or paired sample t-test. So when it is applicable, first of all. So as the name is suggesting that it is a dependent sample t-test. So dependent, or it is also known as the paired sample. Paired means we are pairing the groups of variable as before and after. We are pairing the groups of the variables as before and after design. So some event we are comparing, and before that event and after that event, what is the significant difference that we are comparing here? So two groups are matched in some way. Typically the same people are in both groups before and after. Say for example, the finance people may want to compare the effect of the mergers and acquisitions. So they may identify that certain variables, performance, say for example, of the organization before merger and after merger. So same data we are comparing before and after the merger. So say for example, we need to identify some base year. So base year will be the year in which the merger or acquisition has happened. Now before that and after that, in this way we need to compare. Say for example, the merger is taken place at the year 2000. So base year 2000. So 2001 data will be compared with 1999. 2002 data will be compared with 1998. Like this, we need to prepare two columns and we need to compare the data. So this is how we can go for before after comparison in the case for dependent sample t-test or paired sample t-test. Both the names are same. Now let us do with SPSS. Let me share the screen for the SPSS dependent sample t-test. Now what are the data? So data are available before training and after training.
and it is available for number of productive daily sales call before and after the training. So some training is given, and what was their daily sales, productive sales before that training, that is measured, and after the training, that was measured, and then we are comparing before and after, like this. Before training and say for example, before attending this refresher course, you have been given the certain test, and then after attending this refresher course, the same test is given to you, and your marks in the test before training and after training, before refresher course and after refresher course, what is the significant difference? So that we can compare with before after data. So any situation where you would like to compare your before and after data, at that time you can go for a paired sample or dependent sample t-test. Now you are aware that as this one is the parametric test, so it is compulsory to test the normality. So let us test the normality. So to test the normality, we need to click on analyze descriptive statistics and explore. Now whichever variable we would like to test the normality, we need to consider into the dependent list. We need to click on statistics. We need to click on outliers. We need to click on plots. This is the most important tick mark, normality plot with test. Additionally, we can see the histogram. We can click on continue and OK. Let me share my screen for output window. Now, this is our result. This test of normality, this we need to see. Test of normality. Now, this Kolmogorov-Smirnov test, these significant values are given, and for Shapiro-Wilk test, these significant values are given. What was our null hypothesis? If you do remember, for test of normality, the hypothesis is that the variable is normally distributed. What was the hypothesis? The variable is normally distributed. So we can see the result case test, the p-values for both the tests 0.038, 0.036. So we reject the null hypothesis according to KS test. For Shapiro-Wilk test 0.161, 0.057. So result is we fail to reject the null hypothesis. Now one test it is saying that you reject, and another test it is saying that you fail to reject. What should we do? So according to the thumb rule, that if your sample is small, then rely on the Shapiro-Wilk test. And if your sample is too large, and large they have defined as maybe greater than 2000. So if your sample is too large, greater than 2000, then rely on the KS test. And if your sample is small, then rely on the Shapiro-Wilk test. So we'll here our sample size in this case it is only 25. So we'll consider the result for the Shapiro-Wilk test, and as both the p-values are greater than 0.05, so we'll conclude that the data are normally distributed. Both variables before and after are normally distributed. Now sometimes what happens that we are giving so much importance to normality, and when the normality is not achieved, then we try to transform the data sometimes. You must have heard some log transformation, 1 upon x transformation, square root transformation, like this. So basically we are transforming the data in such a way that after transformation it may become normal. So to achieve normality, sometimes we go for a transformation. Now say for example, in this case, you want to go for a transformation. So if one variable is normally distributed and another is not normally distributed, what will you do? Suppose you are applying log transformation, then equally log transformation you need to give to both variables. Right? Always give to same types of transformation to both variables. Right? It is not like that if one is normally distributed and another is not normally distributed and you give only log transformation which is not normally distributed. So always give the equal transformation to both your variable. Then only it will be comparable. Here, as both variables are based on Shapiro-Wilk test, we are confirming that it is normally distributed, so nothing to worry. And we can conclude that these variables are normally distributed and it is suitable to run the paired sample t-test. Now, as the histogram also, we can see the histogram also looks like a normal distributed curve, right? Though we discussed earlier that in practice, practically we'll never get the perfect normally distributed data, but it is very nearer to normal, and Shapiro is also confirming this. This is a before variable. We look at the after one. Yeah, it is almost perfectly normally distributed. You can just see the histogram and it is a normally distributed, right? So based on histogram also, based on Shapiro-Wilk also, based on skewness and kurtosis, let us see. Skewness is perfectly 0.000 normal in both cases. And kurtosis is minus 0.6 for before and minus 0.58 for after. Right? So both values are within the range of the recommended value. So we can conclude that yes, the data are normally distributed and it is perfectly okay to go for parametric test, that is paired t-test in this case. So now let us apply paired t-test. To apply paired t-test, we need to click on analyze, compare mean and paired sample t-test. Now before variable, we need to consider as variable 1. After variable, we need to consider as variable number 2. And we need not to do anything and just click OK and our result is available here. We can see this one paired t-test result. So the first table that we have obtained for t-test is a descriptive one. Mean and sample size and standard deviations are available. So before training, what is the mean? 3.40. So on an average, they are having the daily productive sales calls 3.40 when the training was not given. And after the training, what is the situation? It has improved to 6. So whether is it a significant improvement or not? From 3.4 to 6, is it a significant improvement or not? Or is it just by chance? Whether the training is effective or not, that is what we are interested. So we require a p-value, but before that, what is our null hypothesis? So null hypothesis in the case of paired t-test is that there is no significant difference in the daily productive sales before and after training. There is no significant difference in the daily productive sales before and after the training. So this is the null hypothesis that we are testing. What is a p-value? So it is available in this table called paired sample t-test. So the first value, it is the paired differences, right? So minus 2.60 is the paired difference between the mean. How minus? 3.40 minus 6. So it is minus 2.60. It is minus 2.60. Why minus? Because the second mean is higher than the first mean. So it is a minus. Now what is the T calculated? T calculated is minus 7.50. Now if you remember in our earlier case, smaller the T value, larger the P value. Smaller the T value, larger the P value. And smaller the T value, larger the T value, smaller the P value. So here, as the T calculated is greater than 1.96, so our P value is automatically less than 0.05. And as it is 7.50, very large significant difference. So the P value is almost 0, 0.0000, maybe after that maybe some values will be present, but it is almost 0, 0.000. So we are rejecting a null hypothesis, and null hypothesis is that there is no significant difference in the daily productive sales before and after the training. So we are rejecting it and we are confirming that yes, there is a significant difference. But our ultimate objective is to conclude it for the effectiveness of the training. See, P value which is less than 0.05, it indicates a significant difference, not necessarily improved. It is not necessarily indicating improvement. It is just indicating a significant difference. How do we understand this? If the mean has reduced, suppose after mean has reduced, then before mean, then also it is quite possible that your P value will be less than 0.05. So 0.05, less than 0.05 P value, it indicates a significant difference. And significant difference is not necessarily it is indicating improvement. So then how do we confirm the improvement? So to confirm the improvement, obviously by default, you can look at the mean value and you can conclude that yes, the difference is significant, 3.406. So there is an improvement. So from number one, from mean value, you can conclude. Number two, obviously, if the mean difference is negative, you can confirm the improvement, because the second one is negative. So if the P value is less than 0.05 and your mean difference is negative, you can confirm the improvement. And third one, if your T calculated is negative, then also you can confirm the improvement. So with respect to this P value, if your P value is less than 0.05, then after mean greater than before mean indicates improvement, mean difference negative indicates improvement, and T calculated negative also indicates improvement. So in this way, multiple ways we can see the improvement. Now here also 95% confidence interval of the mean difference, and it is minus 3.31 to minus 1.88. If you remember, if the both these range of the values are negative, what does it indicate? A negative mean difference here, what does it indicate? After mean is higher than the before mean, and probability is 95%. So we are confirming that there is a 95% probability that the training will be effective, because both the lower and upper values are negative. So we are confirming that uh, the training is effective with the probability of 95%. Earlier, in the case of independent sample t-test, what was our result? That one value was negative and another was positive. If we go back to this one, this is the independent sample t-test that we discussed, right? So in that case, one value was negative and another was positive. So then what was our conclusion? Our conclusion was no significant difference. because we had 0 is in between. So that was the reason that we concluded that there is no significant difference. And this p-value we had observed 0.707. So for the t-test, we conclude that there is no significant difference. And this was the 11th test of equality of variance we observed. So as this 0.884, this p-value was greater than 0.05. So we concluded that we failed to reject the null hypothesis for this test, and we concluded that equal variances are assumed. So row number 1, then we interpret like this. So these two tests, t-test, independent and dependent, we can understand like this. Now the third and last type of t-test is one sample t-test. So let me share my screen for one sample t-test. For one sample t-test, first of all, when we can apply the one sample t-test. So one sample t-test can be applied for unknown parameters, requires t-test comparison of unknown parameter to a specific value. Now it is the comparison of some specific value to the sample mean, and this specific value is a benchmarking value. So here m and mu 0 that we are seeing in the equation, that has been compared. M is your sample mean and mu 0 is some benchmarking value. So if we do not have this benchmarking value, then we cannot go for one sample t-test. We must have some benchmarking value to go for this one sample t-test. So basically we suppose some manufacturers are claiming certain lifetime of a product or certain claims are there. So to test those claims, we are collecting some random samples and then we compare our sample mean with the standard benchmarking value, and then we are testing it for the significant difference. So let us do it with SPSS. Let me open the file first of all, one sample t-test. This is a variable of interest, weight underscore gram. There is a standard product and whose weight is 500 gram. So benchmarking value is 500 gram. And we collected some samples, 46. And our interest is whether the sample mean is significantly different from 500 or not. That is what our interest. As it is a parametric test, we need to check the normality. So we need to click on Analyze, Descriptive Statistics, and now you all are aware, Explore. We need to shift the weight underscore gram into the dependent list. Statistics, outliers, continue, plots, normality with plot, histogram, continue, and okay. And our result is ready. Let me share the result file also. This is our test of normality. We already discussed that when the sample size is small, we need to rely on Sapir-Whorf. So 0.065, it is greater than 0.05, or we have to confirm the normality, and it is appropriate to go for a parametric test called one sample t-test. So now let us apply. Let us click on Analyze, Compare Mean and one sample t-test. Let us shift this variable into weight underscore gram. Now this is important. Test value. Every time, whenever you apply this one sample t-test, your test value will be different. This time our test value will be 500. Why 500? Because it is the standard benchmarking value in our case. So every time, whatever your benchmarking value, according to this value, you need to substitute here. So I have already substituted 500 and then click just OK, and your result available. What is our null hypothesis? Null hypothesis is that
there is no significant difference between the sample mean and standard benchmarking value. It means that there is no significant difference between the sample mean, which is 500.001, and standard value, which is 500. So whether the mean is significantly different from 500 or not, that is what we are testing. What is our p-value? 0.049. So we reject our null hypothesis, because as the p-value is less than 0.05, you have to reject your null hypothesis. So as the p-value is 0.049, so we reject the null, and it can be understood as that there is a significant difference between sample mean and 500. So your sample mean is significantly different from 500. Though very small, narrow difference, but then also we conclude it as a significant difference. So participants, in this way we understood the three types of t-test: independent, dependent, and one sample t-test. Where independent sample t-test we understood as comparison of two independent means. It can be gender, it can be respondents from the two cities, states, like this we already discussed. Second one is the dependent or paired sample, where we compare before and after data. And one sample t-test we compare with the sample mean with some standard benchmarking value. And with respect to all these three parametric tests, we also understood that before going for this parametric test, we need to go for testing of the assumption, that is normality. If these data are normally distributed, if these variables are normally distributed, then only it is appropriate to go for parametric test. So we need to, first of all, the procedure is like that: test the normality. If it is found okay, go for parametric test. But if it is not normally distributed, then what should we do? Then switch to the non-parametric test. That will be our next session for the discussion. So thank you all.